Here I have tried to summarize the aim or the objective of the reduction formulae or integration by successive reduction, as we said before. Reduction formula and integration by successive reduction are one and the same thing, two terminologies meaning the same thing. The objective is, I think, clearly summarized in this particular line, where we say that we take an integral function of x having n as an index. It could be cos x to the power of n, it could be cos of nx, it could be e to the power of mx, whatever, and make that depend on or state that integral in terms of same function, same type of function, but the index n jumps down by one notch or two notches. Sometimes we will see in very special cases that the index climbs up one notch, but that is not a problem, because the climbed fellow can be renamed and that will be in terms of a reduced index. But in general, we find that f x, and this is the index that is contained inside the function, the integral is made to depend on a very similar looking integral in which the index reduces by one or two notches, and then carry out an iterative process, because this, supposing we say that there is a reduction by two notches, then f x n depends on f x n minus 2, f x n minus 2 will depend on f x n minus 4, and so on, as we have seen in the example earlier. So that is the real flavor of integration by successive reduction. We will now take up another problem, and we will see how to use reduction formula also in the context of definite integrals, which we have not done so far. The next integral I will put up on the board is again a very simple looking integral. In fact, it is quite a simple integral, but more than evaluating the integral, it is put up so that we can understand the flavor once again of the process of integration by successive reduction. And it is appreciated by now, I hope, that it is a iterative process, repetitive. Now let us say how we would like to evaluate an integral of the form cos x to the power of n. Again, as usual, we term it as I sub n. This is this n. So if this is 4, this is cos x to the power of 4. Now let us see what we can do. We can write this as the integral of cos x to the power of n minus 1 into cos x dx. Now, this can be treated in terms of integration by parts. So, this we will take as the first function, and this we will take as the second function. So, applying the rule of integration by parts, this equals to first function cos x to the power of n minus 1 unchanged, integral of cos x, that is sin x, minus the derivative of cos x to the power of n minus 1 into the integral of the second function sin x whole integrated with respect to x. This is quite a proper application. First function unchanged, integral of second, minus derivative first function into integral of second, the whole product being integrated with respect to x. So this is equal to, as we see here, we will not write this again and again, this drops down, minus integral of, take a derivative of cos n minus 1 x. This is n minus 1 cos x to the power of n minus 2 into minus sin x, that is applying the chain rule, into sin x and dx. There we are. First term drops down. Derivative of this is n minus 1. There is a minus sign here. Cos x to the power of 1 reduced into d dx of cos x is minus sin x, and this fellow comes out here. So let's see, we have the first term again dropping down. There is a minus here, there is a minus here, so that makes it plus integral n minus 1. I think we can put the n minus 1 right out here. Cos x to the power of cos n minus 2x into sin square x is 1 minus cos square x. This is nothing but drop down man plus cos x to the power of n minus 2 multiplied by n minus 1, that is nothing but n minus 1 times I n minus 2. That's it. And again minus n minus 1 minus n minus 1 times, if we multiply these two and take an integral, that is nothing but I sub n. So here we are, we have I sub n is equal to the first term that drops down plus n minus 1 I n minus 2 minus n minus 1 times I sub n. We will just retain this and rub out whatever we have on top, keeping in mind that the fellow who has been dropping down from top is nothing but cos x to the power of n minus 1 into sin x. So we write that down and then rub out what is appearing later. So we now have I sub n is equal to cos x to the power of n minus 1 sin x plus n minus 1 I n minus 2 minus n minus 1 I sub n. Now we are closer to home, although we have not reached home as yet. One or two more steps and we will be home. What we do is now we transpose that term to the right and write. Transposing that means I sub n is common. This is 1 plus n minus 1 is equal to cos n minus 1 x sin x, it's nice, plus n minus 1 sub I sub n minus 2. Now this is n I n, this implies I sub n is equal to cos n minus 1 x sin x divided by n plus n minus 1 by n I n minus 2. There we are. So we see that I sub n depends on, of course this term is common, plus this factor into I sub n minus 2. So I sub n depends on I sub n minus 2. Now we will invoke limits. and see how we can also apply the reduction formulae to get integrals with limits. Supposing we say let j's of n be nothing but 0 to pi by 2 cos n x dx. In other words, j's of n is i's of n with limits. This implies j's of n will be equal to cos n minus 1x sin x divided by n, limits 0 to pi by 2 plus n minus 1 over n j of n minus 2. Now here we have the first term trapped between two limits 0 and pi by 2. First one is applying a limit of pi by 2 on this expression. The cosine of pi by 2 is 0. The sine of pi by 2 is 1. So the first limit applied here generates 0. The second limit makes this particular fellow as 1, but this particular fellow as 0. So the important thing to realize is that this term with limits just vanishes, and we get a result in which we write that j's of n is nothing but n minus 1 over n j's of n minus 2. We will capture this on top and work a little more so that we see how one can get to the value of 0 to pi by 2 cos x to the power of n for different n, odd and even, whatever. So we just keep the last line there and rub out whatever is appearing on top. So we take this on top and see what happens. J of n is equal to n minus 1 by n j of n minus 2. That's it. Now, when we say j of n minus 2, each n here has to be replaced by n minus 2. So this becomes equal to n minus 1 by n. Replace every n here by n minus 2. So this becomes n minus 3 by n minus 2 j of n minus 4. And j of n minus 4 can be replaced by another expression depending on n, which we will write just now. This is nothing but n minus 1 by n minus 3 by n minus 2. It is easy to see that this term will be n minus 5 by n minus 4. J of n minus 6. So this process can go on, and ultimately the result that will be here, if n is even, then the final term will be j naught, and if n is odd, the final term will be j1, j of 1. Now j naught will be equal to nothing but 0 to pi by 2 cos x to the power of 0, and that is pi by 2. J1 ultimately be nothing but 0 to pi by 2 cos x, that is nothing but 1. So, if n is even, then there will be a factor at the end that is pi by 2, otherwise it will be a number that is without pi by 2. So, this brings us to the end of an integral of the form cos x to the power of n, evaluated as an indefinite integral as well as a definite integral.